Now that we've talked about oscillations, we can start talking about waves. And there are two different wave types. So two types of waves. The first type, the type that we're going to be talking about now for a while, is mechanical waves. These are like the waves that you can see in the world, water waves, waves along strings, springs, that kind of thing. And mechanical waves require some kind of material, some kind of medium to transfer along. You know, I just said these examples are water, strings, springs, and those are the things, those are the mediums, the media that these types of waves transfer along. The water, the string, the spring. That's required for mechanical waves. So these need some kind of medium for the wave to propagate. The other type of wave that we will get to later is electromagnetic waves. They have some characteristics in common with mechanical waves, but these don't need a medium to transfer through. They can transfer through empty space. And that's very good news for us because all of the energy and life on Earth comes from electromagnetic waves transferring through empty space from the sun. So we're going to start with mechanical waves. I gave a few examples. One example that I didn't mention there is sound waves. Those are mechanical waves that transfer through air, or they can transfer through water or whatever. And we'll get to those eventually, pretty soon. And those are the ones that have important medical applications, like ultrasound. But we're going to start with some other types. Mechanical waves can take two forms. Transverse waves and these are waves where the oscillations of points along the wave path are perpendicular to the path. An example of that would be a wave moving along a string. If you took a photo of a wave moving along a string, just a snapshot at a single instant, you'd see something that looks like this. And what's happening is that at each one of these points along the direction of motion of the wave, the particles are oscillating perpendicularly to that. The second type of wave is a longitudinal wave. And these are cases where the easiest way to visualize this is with sending a pulse along a slinky in the direction of the slinky. You know, the slinky spring thing. They still make those. So if this is a slinky, and you send pulses down the slinky in this direction, what you would see is areas where the spring is stretched out and areas where the spring is compressed together. And what's happening is that each point on the spring is oscillating parallel to the direction of the wave. And so these are oscillating in this direction. And so the key difference between these things, these two types of mechanical waves, is whether the oscillations of points are parallel or perpendicular to the direction of the wave. I have a YouTube video queued up here that that'll help you visualize this.
In this video, we're going to look at two ways they can be classified. Waves are produced as a result of vibrations and can be classified as transverse or longitudinal. Whether they are transverse or longitudinal depends upon how the particles are made to vibrate as the energy passes. Let's look at longitudinal first. This is where the particles vibrate parallel to the direction in which the wave of energy is travelling. Notice that the ends of the slinky don't ever leave the hands holding them. It's only the energy that travels. The places where the coils or particles are bunched together are called compressions. Where they are furthest apart are called rarefactions. An example of longitudinal waves is sound. When a drum is struck, the drum skin vibrates, which causes the air particles next to it to vibrate. This causes the next air particle to vibrate, then the next, and so on until the vibration reaches the ear, causing the eardrum to vibrate. The vibrating air speeds away from the source, creating a sound wave. Let's look at another type of wave, transverse waves. The hand moves up and down, as does the slinky, but the wave itself moves from left to right. So the particles vibrate at 90 degrees to the direction that the energy is moving. We can simply think of it as, in longitudinal waves, the hand pulses horizontally, pushing and pulling, and the wave energy also moves horizontally, back and forward. Whereas in transverse waves, the hand moves up and down, but the wave energy still moves horizontally. Again, the ends of the slinky never leave the hands holding it. It's just the energy that moves along. Transverse waves are usually used to show the wavelength and amplitude. Pause the video and see if you can remember how to label the amplitude and wavelength.
So that's how transverse and longitudinal waves differ from each other. But in a lot of ways, they behave the same. And the key thing to remember about waves is all waves transfer energy through space without transferring material through space. So material does move, but it only oscillates back and forth. It doesn't, the wave can move a long distance. The particles that the wave travels through don't move permanently. So waves transfer energy through space without transferring material. If you think about, he was sort of getting at this in the video. When a wave passes through a slinky, the energy moves from one side to the other, but the hands are still holding on to the slinky. That spring is not actually moving through space. It's not the material that's carrying that energy. It's energy being transferred from one particle to another, and it's the energy that moves. That's why maybe you've noticed if you ever drop a frisbee in the lake and you think like, oh, I'm going to throw a rock near it and the waves are going to bring the frisbee back to me. Well, that doesn't work because the waves, even though the waves move from where you drop the rock out, actual water doesn't move from where you drop the rock out. All that moves is energy from particle to particle. Waves are related to oscillations in two ways. This is why I talked about oscillations first before going into waves. First, waves are caused by an oscillation. You know, in order to make a wave move along a slinky, you have to oscillate your hand back and forth. And second, each point, I'm going to call it each material point along the path of the wave oscillates. And so that's why you're going to see that a lot of the terminology that we're using for waves and a lot of the analysis we do looks very familiar from talking about oscillations of particles. The waves that we're going to deal with are going to be sine function related waves. So we'll talk about sinusoidal waves. In a way, you might think like, oh, that's pretty simplistic. You know, no actual waves are really as simple as just a sine wave, and that's true. However, for one thing, this is mathematically the simplest one to deal with, and so you can understand a lot of the behavior of waves by thinking about sinusoidal waves. And then the other thing that's kind of surprising, kind of amazing, is that no matter how complicated a wave is, you can construct that wave as a sum, usually an infinite sum, of sinusoidal waves. So no matter how complex, you know, like some kind of beautiful sound is, that sound can be broken down into infinitely many sine waves. And so this analysis of sinusoidal waves is very applicable to other waves as well. So let's start by defining some key terms related to waves. The first one is the wavelength. And this will be represented by the Greek letter lambda. And the wavelength, imagine if you take a snapshot, so imagine a wave traveling along a string, a transverse wave. If you take a snapshot of that, it would look like a sinusoidal pattern. And if you measure the physical distance between repeating parts of that wave, how far in distance it takes for that wave to repeat, that's the wavelength. So if you take a snapshot, that's the distance for the wave to repeat. The SI units for wavelength are meters. Next, we're going to talk about two things that are familiar from oscillations. And really what we're talking about here are the period and the frequency of the oscillations of individual particles along the path. So first, the period. I'm going to use the Greek letter tau for that. You're going to learn a lot of Greek letters in this class. And the meaning of this is if you watch the motion of a single location, along a single location, along the wave path. That's the time required for the oscillation to repeat. Just like it has the exact same meaning as it did for oscillations. That's because it is a measure of an oscillation of a point. The SI units for the period are seconds. And then related to period, you could probably guess what the next thing is I would talk about. That's frequency. These are really just two ways of saying the same thing. The frequency is a lowercase f, and the frequency is just 1 over the period. And remember that the frequency tells us how many cycles repeat in some unit of time, how many full cycles happen in some unit of time. The SI units for frequency are 1 over seconds. You can tell that from the equation, and we give that the name Hertz. And the last term that I want to bring up now is one that connects these two ideas, one being period or frequency, and the other one being the wavelength. And this is the wave speed. This is the speed of wave propagation along its path. And the SI units for wave speed, well, any speed is just going to be meters per second, and that's what this is. And maybe the most important equation that we're going to see with this wave stuff is that these quantities, these terms are related by an equation or a pair of equations that I'm going to give you. So these are related to each other. You can remember this equation as distance equals rate times time. That's really what this equation is saying. So by distance, I'm talking about the wavelength. And that's equal to the rate, the wave speed, times the time, the period. And so it's easy to remember that equation if you remember distance equals rate times time. This can also be rewritten equivalently. Since 1 over the period is equal to the frequency, you can write this in the way that you see more often, which is the wavelength is equal to V over F. Okay, let's see how to use these in a calculation. So an example. So let's say that we have a 25 hertz wave that travels a distance of 2 meters in 0.6 seconds. You can imagine this wave traveling along a string. And we want to know what's the wavelength. Well, we're already given that the frequency is 25 hertz. The wave speed we can come up with from the distance and the time. So the wave speed is 2 meters divided by 0.6 seconds, which gives you 3.3 repeating meters per second. And now we can use the fact that the wavelength is equal to the wave speed divided by the frequency. So that's 3.3 repeating divided by 25 hertz. All of these are SI units. And we come up with a wavelength in SI units, which is 0.13 with threes repeating meters. All of this information is contained in a function called the wave function. And the wave function, when you look at it, is going to look very complicated, but I'm going to sort of try to help you break it down and just pick out the important information from it. So all this information is contained in the wave function. I'll spell it out. And the form of the wave function is y as a function of the independent variables x and t is equal to a, the amplitude, times the sine of 2 pi over the wavelength times x minus 2 pi v over the wavelength times t. And you could write this in a more simplified form, although I find this form to be the most helpful. But you could write this as amplitude times the sine of 2 pi over wavelength times the quantity. Let me clean that up so you don't think that's an x. Times the quantity x minus vt. Okay, so what do these things mean? 2 pi, those are just numbers. You know what the wavelength, lambda, and the wave speed v mean. What are these x and t? X is the location along the path. So you can think of that as the original position of the string or whatever the medium is you're looking at. T is the time. And then y is the position of the desired point along the path. At the time t. So this wave function can tell you how that point that you're interested in is oscillating at that instant. And you can use this function to describe transverse waves or longitudinal waves. The only difference is in a transverse wave, this y represents a motion perpendicular to the wave path. And in a longitudinal wave, it represents a position parallel to the wave path. I said that A is the amplitude, so you can think of that as the amplitude of individual oscillations of the points along the path. So the first thing I want you to think about is which direction is this wave moving? We're talking about motion along a line, so it's either going to be in the positive x or the negative x direction. And in order to make sense out of this, think of giving the time some small positive value, and think about what has to happen to the x for all the stuff in parentheses to stay the same. that's going to tell you the direction that this wave is moving. So for a small positive time, the question is, does x have to be a small positive or a small negative number for the expression in parentheses to remain the same? If positive, then it's moving in the positive direction. And if it's negative, it's moving in the negative direction. So basically what you're doing is seeing after some small amount of time goes by, does the peak, say you're following a peak of this wave as it moves in one direction or the other, has this peak moved in the positive x direction or the negative x direction? So we'll see some examples that use that. One thing that I want you to notice as you fiddle with this wave function is that sine, it's called an odd function. And what an odd function means is that no matter what theta is, the sine of negative theta is equal to negative sine of theta. Okay, and so we're going to use this fact sometimes to simplify these things. Okay, so let's do an example thinking about the wave function. Let's say that we have a wave function that's 0.15 times the sine of negative 8x plus 15t. And we want to know the following things. What's the direction that the wave is propagating? Second, what's the wavelength? And third, what's the frequency of this wave? I'm going to start by getting this into a form that we're more familiar with by using the fact that sine is an odd function. So I'm going to rewrite this as y equals negative 0.15 times the sine of positive 8x minus 15t. So I just took, I multiplied the stuff in parentheses by -1, and then I multiplied the sine by -1. And now we can think about the direction this is moving. If we take a small positive t value, then the stuff in parentheses is going to become a little more negative. And in order to keep it the same, we need the 8x term to become a little more positive to counteract that. And so what we see is that the direction is positive x. Okay. Second, the wavelength. Well, we're going to use the form of this wave function to answer this question. So we know that the thing multiplied by the x in the wave function here is -8. We also know from the form that I gave you for the wave function that the thing multiplied by x has the form 2 pi over lambda. So I'm going to set this -8. Wait, why did I use that negative? I'm going to use the reason that I put the that I used the odd nature of the sine function is so that this would be positive, so we could compare more easily. Okay, so positive 8 is equal to 2 pi over lambda. And now we're just solving for lambda. You know, lambda is equal to 2 pi over 8. And so the wavelength is equal to 0.785 meters. So if you took a photo at an instant of this string, you would see the pattern repeating itself every 0.785 meters. Now we want to calculate the frequency, and we're going to really use the same thing. This time we're going to use the one with the t. So we know that 15 is equal to 2 pi v over lambda. So that's 2 pi v over 0.785. And that lets us calculate v. So v in this case comes out to be 1.875 meters per second. Well, what does that do for us? We're not trying to calculate v, we're trying to calculate the frequency. But remember, these problems are almost always going to, at some point, use these two key equations that I gave you, relating the wavelength and the wave speed and either the period or the frequency. So now that I have both the wavelength and the wave speed, I can calculate the frequency. The wavelength is equal to the wave speed divided by the frequency. And so 0.785 is equal to 1.875 divided by the frequency. And so we get a frequency of 2.387 hertz. Well, what if we wanted to figure out what a snapshot of this wave would look like at a given instant? So let's come up with a new question here. What was that? Part C. Let's say that we have a part D. So for another part now, let's say that we want to figure out what the oscillation of a point on this path looks like. So we're going to choose an x, and I'm going to choose x equals 0 just to make this simple. And we want to know, what does a y versus t graph look like for this oscillation? You know, each one of these points is just oscillating. Well, we can go to this wave function and set x equals 0. And what we get is that y is equal to negative, what was it? 0.15 sine x is equal to 0, so in the parentheses we just have negative 15t. And I can rewrite this again using the fact that sine is an odd function. So this comes out to be positive 0.15 sine of 15t. And that is the position of this point as it oscillates over time, where this point is our x equals 0 point. So what would this look like? We know that the amplitude is 0.15. We already figured out the frequency, so we could come up with the period that way, just as 1 over the frequency. Or we could, maybe just to jog your memories, remember that the way we come up with the period is just to say this stuff in parentheses is equal to 2 pi and just solve for what t is. So t is equal to 0.419 seconds, and that's our tau, or period. And now it's easy to plot this function. If we have y versus time, this is a positive sine function, so it's going to look something like that. This sine function repeats here. And the amount of time it takes to, whoops, I did that like in the wrong spot. It actually repeats here. You're just looking for where that pattern repeats. And it repeats after 1 period. So that happens at 0.419 seconds. And since the amplitude is 0.15, the top of this graph is going to be at 0.15 meters, and the bottom is going to be at negative 0.15 meters. So that is a position versus time graph of the oscillation of this single point at x equals 0. Okay, now we're going to talk specifically about a transverse wave along a string. There are a few other things that we know about that. You can think of this as like a guitar string, a wave traveling along a guitar string or something like that. Okay. And I'm not going to derive these things. I'm just going to give you these equations and show you how to use these. The derivations are pretty messy. But the speed of a wave moving along, of a transverse wave moving along a string, is equal to the square root of the tension of the string divided by the mass per unit length. Okay, so this is the equation. T is the string tension. If you're in SI units, this tension is going to be in newtons. And mu, Greek letter mu, is the mass per unit length of this string. And the SI units for that are going to be kilograms per meter. So this is the first fact that we have for transverse waves along strings. And the second fact that we have, you can imagine how horrible this derivation is the power. Now, okay, power is related to energy. And at the start of talking about waves, I was talking about how waves transmit energy over a distance through space. Power is the energy per unit time. And so what we're measuring is per unit time, choose a spot on the string, how much energy is passing through that point. Okay, so this is the rate of energy transfer through a point on the string. So this calculation is the power. is equal to 1/2 times mu, that's the mass per unit length, times an omega squared. We've used omega for angular velocity in rigid body problems. This is a new thing, and I'll tell you what that means in a second. And that's squared times the amplitude squared times the wave speed. Okay, so this is the power. This omega is equal to 2 times pi times the frequency. And the SI units for power are joules per second because it's a rate of energy, and we give that its own name, watts. So like when your light bulb is rated to 60 watts, that's saying it's using 60 joules of energy every second. And we denote that with a capital W. Okay, so these are the two new equations that we have for transverse waves along a string. Oh, I do want to point something out. So if you think of the strings on a guitar, the upper string is thick, and then little by little they get thinner as you go, and so on. Well, let's think of a ukulele so I don't have to keep drawing strings. But what's happening with these strings is that the mass per unit length as you go higher is going up. And you can see that that lowers the wave speed. We don't have a way to connect that to frequency yet. We'll do that soon. But you can see that if you just play the strings of a ukulele, you have a high wave speed if you assume that the tensions are all somewhere in the same ballpark. The higher string has a faster wave speed, higher frequency, I mean, the one closest to the ground, and the one farthest from the ground, highest up, has a lower wave speed. Okay, so here's an example problem. So let's say we have a 2-meter long string with a mass of 0.3 kilograms, and the tension in the string is 120 newtons. And let's say that the frequency of oscillation is 80 hertz, and the amplitude of the oscillation is 6 centimeters, so 0.06 meters. And we want to calculate the wave speed. We want to come up with the wave function. And then last, we want to calculate the power of this wave. Okay, so first, to come up with the wave speed, we know that the speed is equal to the square root of the tension divided by the mass per length. We're given the tension. We can come up with the mass per length. Okay, so the tension is 120 newtons. The mass per length is 0.3 kilograms divided by a length of 2 meters. And so that's 0.15 kilograms per meter. And so the wave speed is the square root of 120 divided by 0.15. I'm keeping all this in SI units, so I don't really have to think about the units. And we get a wave speed of 28.28 meters per second. Next, we want to come up with the wave function. And in order to come up with the wave function, remember that this has the form amplitude times the sine of the quantity 2 pi over the wavelength times x minus 2 pi times the wave speed over the wavelength times t. And so we need to come up with the wavelength and we need to come up with the wave speed. We can use the equation that says wavelength is equal to wave speed divided by the frequency. We just calculated the wave speed. This is 28.28 meters per second. The frequency is given. So we're dividing by 80 hertz. And we get a wavelength of 0.354 meters. Okay, so for the first term in the parentheses, our 2 pi over the wavelength is going to be, so 2 pi over the wavelength is 2 pi over 0.354. And so we get 17.77. We've already calculated the wave speed, so now we can plug all this stuff in too. So 2 pi v over the wavelength is, well, we have the wave speed times 2 pi over the wavelength, and that comes out to be 502.58. The amplitude is given in the problem to be 6 centimeters. And so we can finally come up with this wave function. It's a function of x and t, and it's equal to 0.06 times the sine of 17.77x minus 502.58t. Finally, the power. This is just a matter of plugging in numbers. Omega is defined as 2 times pi times the frequency, so that is 502.58. And the power then is 1/2 times the mass per length times this omega squared times the amplitude squared times the wave speed, which we got somewhere, 28.28. And that is equal to 1,928.65 watts. And so if no energy is lost anywhere, the minimum amount of energy that could be provided to create this wave has to be 1,928.65 watts. That's what the oscillator has to be providing to the wave to create this wave.